Okay, the question here is to figure out what the nth term of the sequence is. That means to figure out what the formula is to describe the terms. I think the easiest way to approach these at first is to make a table of values that relates the rank n to the number itself, the term. We want to look for a pattern. Let's ignore the negatives at first and just look for the pattern in the numbers themselves. We can see that we can write each one of these terms as a fraction, and the numerator is 1, and the denominator is a power of 3. Look at the exponents. They form a pattern. When n is 1, the exponent is 0. When n is 2, the exponent is 1. In other words, the exponent is always 1 less than n. So we can write the number itself as 1 over 3 to the n minus 1. To express every second term as a negative value, we can take negative 1 and raise it to the power of n minus 1. If we had started with a negative term, then we could have just said n. And then we can clean it up a little bit. The numerator and the denominator both have the same exponent, so we can bring them together. Call it negative 1 over 3, all to the n minus 1. The next one here, we can see that the numbers are each increasing by 3. So it's like a linear function with a slope of 3. So we can say 3n, and then we just have to figure out what we need to add or subtract to get to the correct value for our first term. Plus 2. So just add 2. This one is a little trickier. I'm going to write this out again as a table of values, n versus the term. So we can see the values start at 1, go down to 0, down to negative 1, and then they start to come back up to 0, go back up to 1 again, and then the cycle repeats. This feels a lot like a trigonometric function. We're going from the maximum to the middle value to the minimum, back to the middle value. It's as if it's a cosine function. So let's draw the cosine function. Cosine starts at the max at 1, and the period is 2 pi. So when the angle is 0, our value is 1. So the first term is like saying cosine of 0. The next term is 0, which is cos pi over 2. The next term is negative 1, which is cos of pi. You can see the pattern here. The next term is again 0, which is cos of 3 pi over 2. And then cos of 2 pi. The next one, it's really just the angles that we're changing. And it looks like each angle is going up by pi over 2. So 2 pi plus pi over 2 is 5 pi over 2. How do we relate the angle to n? If every angle is going up by pi over 2, again, it's like a linear function, pi over 2 times n. But what we need to do is subtract 1 from n before we multiply it by pi over 2. So when n is 1, the angle is 0. When n is 2, the angle is pi over 2. So our formula is cos of pi over 2 times n minus 1. Okay, the following series of questions all ask whether the sequence that's given is convergent or divergent. That will always involve finding the limit as n approaches infinity of the nth term. So we use all our limit tricks. In this one, this is a rational expression. What we want to do is multiply the top and the bottom by 1 over n cubed, because when we do that, we can see that we're left with a 1 over n cubed only that will go to 0. If the limit exists, then the sequence converges. This is another rational expression. This time the highest term in the denominator is n, so we divide the top and the bottom by n, we're going to be left with n squared on the top. 1 over n goes to 0, but we still have n squared. So here the limit is infinity, so the sequence diverges. This expression we'd like to clean up a little bit algebraically. Let's separate 3 to the n plus 2 into two powers that are multiplying one another. 3 to the n times 3 to the 2. So now we have 3 to the n on top and 5 to the n on the bottom. We can combine those together, make it 3 to the 5, and then 3 to the 2 is just 9. We could bring the 9 out in front because it doesn't change with n. Now what's this going to be? 3 to the 5 is a number that's less than 1. Let's think about how this would look if we were to graph it. When n is 1, the term is 3 over 5. When n is 2, the term would be 9 over 25, which is smaller. So we can see as n increases, our terms decrease. This is just like an exponential function, and the limit is 0. It's like an asymptote, a horizontal asymptote. So the limit exists and the sequence converges. Here's another limit that we can treat this as a rational expression underneath the root. So we can multiply the top and the bottom by 1 over n, all under the root, and we'll still get rid of a lot of the n terms that we don't want. So the limit exists and the sequence converges. This question has a rational expression in the exponent, but we could treat it the same way. Let's just clean it up, try to get rid of the n's that we don't like, look for the highest power of n in the denominator, which is n. And then 2 over n will go to 0 as n goes to infinity, so we're just left with e squared. The limit exists and the sequence converges. The next question is an alternating sequence. So let's see if that little rule we saw in the lesson would apply here. If we take the absolute value of the nth term of a sequence and we see that it's 0, when we take the limit as n goes to infinity, then that means the whole thing will also be 0. Let's see what happens here. Taking the absolute value of this expression really just means ignoring the negative 1. So just take off the absolute values, take away the negative 1, and we're left with the rational expression. Multiply the top and the bottom by 1 over n, and we can see that we are left with 1 over 1 plus, now this is 1 over root n. If you're not convinced, let's look over at the side. Root n divided by n. Change it into n to the half divided by n. Use your exponent rules, and there you go. It's 1 over root of n, which goes to 0 as n goes to infinity, so the limit is 1. Okay, well this is not equal to 0, so we can't use this rule here. So let's start again. What is the limit of a sub n? Let's just multiply the top and the bottom by 1 over n. The 1 over root n here is still going to go to 0. So we're left with negative 1 to the n plus 1. That's just going to bounce back and forth between negative 1 and positive 1. The limit does not exist, and the sequence diverges. In this question, the notation is a little bit different, but this just means that the formula for a sub n is ln of n divided by ln of 2n. So what happens if we take the limit? This is going to be infinity over infinity, because ln of infinity is infinity, which is an indeterminate form, so let's use L'Hopital's rule. We take the derivative of the top and the bottom. Remember, the derivative of the bottom is 1 over 2n multiplied by the derivative of 2n, which is 2. So the bottom is 2 over 2n. Now just simplify this expression. Everything here is going to cancel out. The 2's cancel out, the n's cancel out, and our answer is 1. So the limit exists and the sequence converges. Okay, what's the limit of this expression? What does arctan of x look like? Let's draw that. This would be a good time to use the squeeze theorem. We want to build our expression of arctan n over n by starting with arctan of n, stating that it is between pi over 2 and negative pi over 2. Then we divide everything by n so that we have our expression that we want. Take the limit of either side. So the limit of negative pi over 2 over n is 0. The limit of positive pi over 2 over n is 0, because a number divided by infinity is 0. So if the limit on either side of the expression we want is 0, then the one in the middle must also be 0. So our limit exists and the sequence converges. In this question, let's use our log rules. Log of a minus log of b is equal to log of a over b. Now we can simplify this rational expression on the inside by dividing the top and the bottom by n. One over n will go to 0 as n goes to infinity. So this is equal to the ln of 1, which is 0. The limit exists and the sequence converges. This looks a little bit messy. Why don't we take this expression off to the side and just remember how to deal with exponent rules. When we have the nth root of something, it means raised to the power of 1 over n. When we raise a power to another power, that means we multiply the exponents together. Now here's a little fraction, a little rational expression that we can deal with. Again, we want to get rid of the highest power of n in the denominator. So we multiply the top and the bottom by n. Now the exponent's a bit cleaner. It's just 2 to the 1 over n plus 3. 1 over n goes to 0 as n goes to infinity. So our answer is 2 to the 3. Limit exists and the sequence converges.